Hey everybody, Missy here, and today we're going to learn about electron configurations, and that is going to tell us where electrons are located within our atoms or ions. So thanks to Schrodinger, he has developed, or him and his team, developed the model that we use the most today, and in his model, he said that electrons are found in orbitals or clouds, and we are going to spend today learning more about those different orbitals, what their names are, and how we can figure out what the electron configuration is for any given element. So to start with, Schrodinger's luckily based his idea, it's similar to the periodic table. And from the periodic table, we can look at what row that an element is in, and that tells us its energy level. Orbitals are indicated by lowercase letters. There's a s, p, d, and f orbital. Numbers of electrons are shown as exponents. And then we'll talk about how we read it in a couple minutes. So we have this s, p, d, and f orbital, and they have different shapes. And these are, if I pretend that my nucleus is in the center of each one of these shapes, these are the probable locations that the electrons could be in based off of where they are in terms of their energy. The s orbital looks like a sphere. The p has these 6 different lobes. The d has a clover leaf type pattern, and the f is just too complex to draw. You could look it up if you want to. The s orbital can hold 2 electrons. The p orbital can hold 6, d can hold 10, and f can hold 14. In terms of energy, the s orbital is the lowest energy orbital, and the f orbital has the highest energy associated with it. And we'll use this information to help us number some things on our periodic tables. So you can either take your periodic table and you can use like Sharpie or marker or pen to write on it because it's laminated-ish. It's got that shiny paper. Or you could print off a periodic table offline. I went ahead and printed this one off. It's just from like printable images from Google. Doesn't matter. Whichever you use, this just fits better underneath my camera. So the first thing that we're going to do on this is we are going to shift helium over here for the purposes of looking at where its outermost electrons are. Helium stays here. It doesn't actually move, but we're going to push it over just for the purposes of writing electron configurations. Lowest energy orbital is our s orbital, and our s orbital is represented on these first 2 columns of our periodic table. So this we call our s block. We'll call each of these blocks. And if this is our s block, I'm just going to fill in my elements here. And our s orbital is the lowest energy orbital, so I'm going to start by numbering it 1, 2, 3, 4, 5, 6, 7. My next orbital is my p orbital, so I'm going to look at my p block of my periodic table. That is here, and remember that we moved helium over, so that's not part of it. Our p block is these columns of our periodic table on the right-handmost side. Nice straight line. So these is our p block here. And our p block is the second highest energy orbital, so we're going to start by numbering this 2, 3, 4, 5, 6, and 7. Our next orbital is our d orbital, and that is going to be our transition elements in here. So anything in between our s and our p, it comes down there and there. This is our d block. Our d block, or our d orbital, is our third highest energy orbital, so we're going to start by numbering this 3, 4, 5, and 6. And then finally, we have our f orbital, which we can see in our inner transition metals. So all of these are our f block, and that is our 4th highest, so that's going to be numbered by 4 and then 5. And so the cool thing about using our periodic table is that we can read it left to right and identify our electron configurations based off of where things are located on the periodic table. So let's go through some examples together, and you'll start to see the pattern that exists with our electron configuration, and then it'll get easier as we continue to practice. So if I were to look at hydrogen, hydrogen's located here. When we write an electron configuration, we're always going to write the energy level, then the orbital, and then our electrons in it as an exponent. So I have hydrogen is in location 1, then I report my orbital S, and it's the first one over, so it's 1s1. So this is my energy level. My S is my orbital, and my exponent here is my number of electrons. So I have 1 electron, and then we'll talk about valence electrons in a little bit. So if I were to look at helium, helium's located here. Luckily, we don't have to state an electron configuration or location for everything prior to it, just at the end of blocks. So helium's, electron configuration is 1s, and it's the second one over, so it's 1s2. My number of electrons is reported as my exponent, so there's 2 electrons there. Now let's take a look at lithium. Lithium's in this location here. We need to always start at the beginning, so we always start here. You can't see what I'm writing. We always start here with hydrogen, and so we'll have 1s, and we report at the end of the block, so 2, 1s2, and then after that, there's nothing over to the right anymore, because helium we move. So we come to our next round, we have 2s, and lithium's the first one in, so 2s1. So I have 1s2, 2s1. I have 2 electrons in my s orbital, 1 electron in my 2s orbital, so it gives me a total of 3 electrons. Next, I have nitrogen. Nitrogen's over here. Again, we still start at the top left with hydrogen. So I have 1s2, then I come down to my next row, 2s2. Now after that, this is number 4, so I need to go to number 5. So I come straight across my periodic table. So I have 1s2, 2s2, 2p, and nitrogen's 1, 2, 3 over. So 2p3. So 1s2, 2s2, 2p3. Now notice when I write these, there are no commas in here. My letters are lowercase. My initial numbers are large, almost like capital numbers. And then I have my superscripts here of my electrons. Okay, it should look exactly like mine. Don't add commas. Don't put any funky spacing. It should look just like mine. So the number of electrons, 2, 4, 5, 6, 7. Remember that these are atoms, so our electrons equal our protons, which is the same as our atomic number. All right, next is fluorine. Fluorine's just a little further down in our P block in the same row as nitrogen. So again, starting at the beginning, 1s2, 2s2, straight across, 2p, 1, 2, 3, 4, 5. So 1s2, 2s2, 2p, 5. Number of electrons, 2, 4, plus 5 is 9. Next, we have phosphorus. Phosphorus, located here. Again, we start at the top. 1s2, 2s2, straight across, 2p, and this is 1, 2, 3, 4, 5, 6 wide, so 2p6. Now I go down from 10 to 11, so I go to my next row. 3s2, again, I come straight across. 3p, 1, 2, 3. So 3p3. So 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3. And I have a total of 15 electrons. Last example is nickel. Nickel is here in our D block. So again, we start at the beginning. 1s2, 2s2, cross, 2p, 6. Then down to our next line, 3s2, 3p6. Down to our next line, 4s2. And then this one starts with 3, even though it's in the fourth row, starts with 3, 3d, 1, 2, 3, 4, 5, 6, 7, 8. So nickel, 3d8. So I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8. Is that right? Yes. Total number of electrons, 28. Now, valence electrons. Valence electrons are electrons located in the highest energy level. Remember, the energy level is that number on the front. Okay, so my highest number on the front is going to be my highest energy level. In helium, I only have one energy level. So those 2 electrons in my 1s orbital are my valence electrons. Lithium, however, has a 1 energy level and a 2. 2 is higher than 1. There's 1 electron there, so 1 valence electron. Nitrogen has 2 orbitals in the 2nd energy level. So combined in the total electrons in my 2nd energy level, 3 and 2, gives me 5. Same thing for fluorine. 2nd energy level is the highest. 2 and 5 make 7. Phosphorus has the 3rd energy level as the highest. 2 orbitals there, the S and the P. So again, 5. Now nickel, even though it ends with 3D, this 4s comes before it, and this is a higher energy level, 4 is, than 3. So my 4s2 gives me 2 valence electrons. What we can do next is we can draw a diagram that shows where our electrons are within each one of our sublevels. So that is our orbital notation. Orbital notation is because of 3 different principles. We have the Aufbau principle. That principle states that electrons occupy the lowest energy level first, which we saw by electrons being in the 1s level before they were in the 2s or the 2p or the 3s. Pauli's exclusion principle says electron spin must be paired. So that means that our electron spin, we're going to show an electrons by a half arrow. So I'm going to point one up, and so to pair it, it's going to be paired with one pointing down. So this is a pair of electrons. We would never write them both up or both down because that is no longer being paired. They're moving in the same direction. We don't want that. So we want them to be one up and one down. Then Hund's rule says electron spin must be maximized. So that means that electrons are going to fill their own line before they double up. So what does that mean? If I have 3 different lines, so 3 different spots in my orbital for electrons to go, they're going to each want their own spot before they double up. So they would go up, up, up. They would not go up and down and then up. This does not maximize spin. So remember that our electron orbital, our s orbital held 2 electrons. P orbital holds 6. D holds 10, F holds 14. Electrons eventually want to pair up. So that means if I have 2 total electrons, I can only have 1 line. 6 electrons means that I have 3 lines. 10 means I have 5. And 14 means I have 7. Okay. We would label underneath these S, P, D, and F, and then the number in front to show what energy level that orbital was in. Okay, so let's put this into practice. I want to look at my electron configuration and orbital notation for cobalt. First thing we need to do is figure out the electron configuration, and then we can write the orbital notation above it. So I leave yourself a little bit of room so that way we can write the electron configuration underneath and then our orbital notation above it. So if I want to have cobalt, okay, cobalt's here. Its electron configuration for cobalt is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. So I'm going to write them spread out a little bit. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So I left myself a little bit of room here because I'm going to write all of these lines above it. So my orbital notation, 1s2. So s has one line, so I put one line here. 2s, again, has one line. P has 3. S has 1. P has 3. S has 1. D has 5. It's really important that you show the individual lines for the suborbitals within these orbitals, and that you don't just write one large line. Okay, we have to show the individual ones, and we have to label them underneath. Next, I'm going to put in my electrons. Again, I need to put them shown by half arrows. They need to be spinned in opposite directions, and one in each line first before I double up. So my s orbital has 2, so 1 up, 1 down. My 2s has 2, 1 up, 1 down. My 2p has 6, 1, 2, 3, 4, 5, 6. My 3s has 2. My 3p has 6. And it's good to get in the habit of up all the way across and then back down, just so that way when you get to the end, you're already in practice of doing that. My 4s has 2. My 3d has 7. 1, 2, 3, 4, 5. Then we come back and pair up 6, 7. Should look exactly like mine. Up first, down second. So this is my orbital notation, which shows me exactly where all of my electrons are in the individual lobes of my different orbitals. Now at this point, you're probably going, Missy, oh my gosh, please tell me there's a shortcut, and you're in luck. There is a shortcut. We call it noble gas notation because we use the noble gases, which are elements in group 18, to help us shorten up what has to be written. So that means on the periodic table, these elements here in this last column, these are your noble gases. Okay. Those have full shells, right? So everything's full here. We have 2p6 on all of these, 3d10s. Okay. So those are full. Their electrons are all paired. They're very, very happy and very, very stable. They never form ions. So we can use them as reference points. So to do so, we are going to locate the element we care about. Then we are going to move up and over the line above to find the last previous noble gas. So we locate our element, then we move up and all the way over to the right to find the previous noble gas. So anytime we go up and all the way over, we'll find our noble gas. We're going to put our noble gas in brackets, and then we'll continue writing electron configurations for everything that comes after our noble gas until we reach the element that we want. So if my first example is sulfur, sulfur's here. If I come up and over, my previous noble gas is neon. So I'm going to put neon in brackets. Remember that it's a capital first letter, lowercase second letter, and these look like brackets, right? So at 90 degrees here. And then I'm going to write everything that comes after neon before I get to sulfur. So after neon, I come to here, 3s2, straight across to 3p, 1, 2, 3, 4. So I have 3s2, 3p4. For potassium, here, potassium's last noble gas, up and all the way over is argon. So argon gets put in brackets, and then potassium's in location 4s1. So it's much quicker and shorter. You'll still have to write all three of them, right? It's the way for us to show a diagram of the atom and where the electrons are located. But this is one more example of how you could show that. Most likely I'll ask you a question and I'll expect for you to write a Bohr model, fill out an atomic structure chart, write electron configurations, orbital notations, and noble gas notation. So all of those are diagrams of our atom. Finally, we can look at making ions. Remember that ions are made by adding or removing electrons. So electrons are added or removed from the highest energy orbital. Remember that F is our highest, S is our lowest. And then we also have our energy levels. Obviously, a 4 is higher than a 3. Remember when we made Bohr models that we were able to make ions by either adding electrons to the outermost ring or removing electrons from the outermost ring? Well, now we're more specific in that we're adding or removing what are called valence electrons. So remember, our elements become ions by gaining or losing electrons, and they do this to become like noble gases. Noble gases either have a full or empty outer shell, depending upon how the atom gets back to its noble gas notation. So let's go through an example. First, we're going to look at cobalt. Now, we've already written cobalt's electron configuration above here, so I'm just going to go ahead and rewrite that. So for the atom cobalt, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Now remember that we add or remove electrons from our highest energy orbital, or we look at our valence electrons. For us, that is this 4s space here. Okay. Cobalt becomes +2. If it's +2, that means that I lost 2 electrons. Right? Electrons are negatively charged. If I'm gaining electrons, I get more negative. If I lose electrons, I become more positive because now there's more protons than electrons. So I have this +2 charge. I have to lose 2 electrons, and I'm going to lose those electrons from my highest energy level, which in this case is my 4s. So instead of 4s2, I remove those, and I have 4s0. So everything else stays the same. 1s2, 2s2, 2p6, 3s2, 3p6. Now I have 4s0 and then 3d7. So this, to have an orbital notation, again, I label them underneath, 2s, 2p. Hopefully you give yourself a little more room than I did. 3p. I still need to show my 4s, and I'm going to show that it's empty. I'm going to put in my electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, so I just leave that blank, and then 3d7. Finally, we can go ahead and write our noble gas notation. The previous noble gas to cobalt, we look on our periodic table. Cobalt's here, up and over, it's argon. So we put argon in brackets. Everything that comes after argon is 4s2, but for my ion, that's blank. So it's 4s0. So everything of this comes after. 4s0, 3d, 1, 2, 3, 4, 5, 6, 7. And now you're able to show with more precision where your electrons are and also how to do it for ions.